Good day, everyone. We are Group 3 and we are here to present and discuss our topic all about stability information. So, first, this is our title Purpose of the Stability Booklet Understanding Stability in Daily Operations. But before that, let we introduce ourselves. I am Midshipman Kababaro Lawrence D. Together with my co-presenters, we have Caranto Danica, Calma Christian Kurt, Cabanero Renz T, Cabang Chaos Jekyll, and Volante Romberto. So before we proceed to our proper discussion, these are the contents of our presentation. So first, we have the purpose of stability booklet, loading conditions, kg, gm, trim, ballast, free surface effect, examples of calculations, and how officers use stability information in daily operations, and accident linked to poor stability data of Herald of Free Enterprise. So what is a stability booklet? Stability booklet is a document used to ensure the ship's stability throughout operations. It provides essential information regarding loading conditions, trim, ballast, and etc. It helps officers and crew maintain vessel stability for safety. So stability booklet is like a manual for ship stability. It tells us how the ship behaves in different loading conditions and give guidelines on what to do to keep the ship stable. It includes values for trim, ballast, and other calculations. Without it, the crew would be guessing and that can be dangerous. So mahalaga po ang paggamit po ng stability booklet para ma-ensure po natin yung ship's stability throughout operations po.
So, hello guys, I am Michi Puman Danica S from BSMT 3 Alpha. So, I will explain the stability information purpose.
Purpose of stability booklet. Ensure safety operation by maintaining vessel stability in all conditions. Provide guidelines for officers when making decisions on loading, ballasting, and trimming. Helps prevent accident caused by poor stability management. Act as a reference tool for quick stability checks during daily operations. Purpose of stability booklets is critical documents on board a vessel that provide information and guidance to ensure the ship remains stable and seaworthy under all operating conditions. It supports the safe loading, unloading, and operation of the vessel, ensuring compliance with maritime regulation and helps prevent capsizing or losing control. This include the key data like hydrostatic stability curves, loading conditions, and damage stability, and is primarily used by ship's officers, inspectors, and surveyors to assess and manage the ship's stability.
And also, it guides officers in loading and ballasting. Second, it helps calculate draft, trim, GM, and GZ. Third, it keeps the ship compliant with IMO and class rules. Fourth, it provides construction for emergency stability. And the last is, it is used daily for sailing and during voyages.
Contents of stability booklet. Loading conditions. Describe how cargo is distributed to maintain proper stability. Provide sample cargo loading scenarios like ship, full load, ballast condition, heavy cargo, and etc. Showing how stability is maintained under operations. Ship loading conditions is describe how cargo, ballast, fuel, and store are arranged and distributed on a vessel, impacting its stability, trim, and overall safety. Standard loading conditions like a fully loaded departure and ballast departure conditions are assessed to ensure the ship meets stability for safe operation at sea. Key factors is the weight and location of loads hull and strength, and ship draught, depth of submersion of all we are continuous monitored during loading and unloading operation. Overall, loading condition is describe how the cargo distribute the weight and maintain the proper stability of the ship. vertical center of gravity, indicates that height at which the weights of vessel acts. Show the exact point where the vessel weight acts vertically. Helps officer calculate whether the ship will remain upright or become unstable if cargo is shifted. kg is the vertical height of ship center of gravity above the keel. Indicates where the ship weight is concentrated vertically and directly affect the ship's stability. A lower kg means better stability, while higher kg can reduce stability and increase the risk of capsizing. kg change with loading, unloading, and shifting weights on board, so it must be carefully managed for safe operation of the ship.
Contents of Stability Booklet, GM or metacentric height, a measure of the vessel's stability explained by the distance between the center of gravity or G and metacenter or M. A larger GM is equal a more stable but stiff ship's quick rolling. A smaller GM is equal to a tender ship's slow rolling but less stable. Trim. The balance of the ship fore and aft, ensuring even weight distribution. Explain forehead and aft balance. Provides tables and diagrams showing how the ship will sit in the water, by the bow, by the stern, or even keel.
Ballast materials added to maintain the ship's balance, especially during loading or unloading, includes instructions on how ballast tanks should be filled or emptied to maintain proper stability, and trims. Shows ballast exchange plans during cargo operations. So, ballast is a seawater carried in special tank to keep a ship stable, balanced, and safe. It is adjusted during loading and unloading to maintain proper trim and draft, and exchange to prevent spreading marine species. So, the free surface effect. The shifting of liquids inside the vessel that can reduce stability describes how liquids in partially filled tanks move as the ship rolls, reducing the effective stability. Provides corrections values to account for this effect in calculations. So, in short, free surface effect happens when a tank is partly filled as the ship rolls. The liquid inside shifts, raising the ship's center of gravity and reducing the stability or the GM. To correct this stability calculation, add a free surface correction value showing the loss of stability caused by the slack tanks.
At this point, para mas lalo nating maintindihan yung mga contents ng stability booklet, ito yung mga examples po ng bawat contents. So first, we have the loading conditions. So for example, ang given natin is lightships. Meron siyang 2,000 tons at merong kg na 3.0 meters. And merong cargo na 1,000 tons at merong kg na 7.0 meters. So, ika-calculate natin yung total displacement, yung total moment, and yung kg ng lightship and cargo. So, ito po yung step by step. So, sa total weight, ipag-add lang natin yung lightship ng, yung tons ng lightship and ng cargo. So, 2,000 plus 1,000 is equals to 3,000 tons. So, to compute that total moment of lightship and cargo. So, ita-times lang po natin yung tons tsaka meters ng kg po ng lightships and cargo. So, sa lightship, merong 2,000 tons. Ita-times lang po natin ito sa 3.0 meters para makuha po natin yung 6,000 tons per meter. So, sa cargo din, 1,000 tons times 7.0 meters para makuha po natin yung 7,000 tons per meter. So, to compute the total moment ng lightship and cargo, ipag-add lang po natin yung nakuhang moment ng lightship at cargo. So, 6,000 plus 7,000 is 13,000 tons per meter. Yan. And to compute naman yung kg natin, for ang formula doon is kg is equal to total moment divided by total weight. So, ang nakuha nating total moment is 13,000. I-divide lang natin to sa 3,000 na nakuha natin sa total weight kanina. So, again, para makuha natin yung kg natin, we have the formula kg is equal to total moment divided by the total weight. So, ang nakuha po natin total moment is 13,000. I-divide lang po natin siya sa total weight natin na 3,000. So, ang makukuha po natin doon is kg is equal to 4.3333. So, ang kinuha po namin dito is 3 decimal point lang para po mas madali po nating yan, para mas madali nating maano. So, ang answer po natin, displacement is equal to 3,000 tons and our kg is 4.333 meters. So, interpretation, adding the high cargo raised the ship's kg to 4.333 meters. So, these simple examples po, nagpapakita po siya ng kung bakit loading conditions are very important. If cargo is not evenly distributed, yung vessel or the vessel will trim either forward or aft. Here, since the aft hold has more cargo, the vessel trims by stern. That's why booklet guides us in balance loading. So, itong example po na ito, nagpapakita po siya ng loading conditions. So, next example, we have
Free surface or effect FSC. So the given is displacement 5,000 tons partly filled tank free surface. Then the second moment of 50 meters ship GM before FSC is equals to 2.0 meters. Then find FSC and effective GM. So we have the steps. So the step 1 is FSC. Second moment divided by displacement is 250 divided by 5,000 is equals to 0.50 meters. So the second step is GM minus FSC. 2.0 minus 0.50 is equals to 1.950 meters. So the answer is FSC is equals to 0.50 meters. Then the GM is 1.950 meters. So the interruption, free surface reduces the effective GM slightly. Monitor partially filled tanks as they lower the stability.
Example, calculations of trim. Ito po yung given, tas yung steps, tas ito yung mga answers. So, paano po ito nakuha? Yung trim, sir, is the difference between the vessel forward draft and aft draft calculated by subtracting the forward draft and the aft draft. Trim calculation is involved a trimming moment, the result of weight being added or moved, which is then divided by the ship MCTC moment to change trim by 1 cm or 1 inch. To determine the change of trim, this change is used to find the final draft of the ship. So, ayun po ang example ng paano mag-calculate of trim po.
So, second to the last examples, we have the ballast. So, for example, a light ship is unstable because the kg is too high. Officer, add 1,000 tons of ballast water at the double bottom, 1 meter above keel. So, ang hinahanap po dito is yung bagong kg niya or yung vertical center of gravity after magdagdag ng weights. So, we have the given ship is equal to 5,000 tons and the vertical of center of gravity is 7.0 meters and the ballast is 1,000 tons at 1.0 meters. So solution, we have the new kg is equal to original ship displacement, which is yung big W, times the center or the vertical center of gravity plus the added weight times the vertical position of the added weight divided by the original ship's displacement plus the added weight. So 5,000 times 7 is equal to 35,000. Then 1,000 times 1 is 1,000. Then divide lang natin sa 6,000. So 35,000 plus 1,000 is equal to 36,000 divided by 6,000 is equal to 6.0 meter. So ballast so the new kg or the new vertical center of gravity after adding the weight pagkatapos magdagdag ng bigat is 6.0 meters. So ballast lowers the vertical center of gravity and makes the ship more stable. So magkakaroon ng stable na ship. So adding ballast reduce vertical center of gravity from 7.0 meter to 6.0 meter, improving stability. So, yun po yung example ng ballast.
Example calculation for GM. So the given is Km is equal to 6.20 m from hydroplastics. Ships kg is equal to 4.10 m. Then find GM. So the step is first the formula is GM is equal to Km minus Kg. So GM is equal to 6.20 minus 4.10, and the answer will be 2.10 m. And interpretation is positive GM of 2.10 m. Ships has restoring ability is stable.
How officers use stability information in daily operations. Cargo operations. Balance cargo. Check kg and trim during loading and unloading. Ballast control. Add or adjust ballast to keep ship steady. Free surface effect. Ensure tanks are properly filled to avoid instability. Rough seas navigation. Adjust speed, route, trim, and GM for safety. Post maintenance. Check stability after repairs or modifications. Emergencies. Use ballast cargo ships to stabilize during flooding or fire. Here are the key takeaway. Officers rely on stability data every day to keep the ship safe and balanced. My explanation on officers use stability information in daily operations is officers use stability information every day to make sure the ship is safe and seaworthy. They check the ship's loading ballast, trim, and GM to confirm it meets stability criteria before sailing. During the voyage, they monitor ballast and free surface effect, adjust trim for efficiency, and ensure the vessel remains within safe limits. Even in rough seas, in emergencies, stability data helps them decide how to counter flooding or cargo ship.
So at this point, this is the examples of accidents linked to poor stability data. So Herald of Free Enterprise, 1987, capsized due to poor stability and incorrect loading, at nagkaroon siya ng 193 lives lost or 193 na nawalang buhay. So ang lesson learned dito highlights the importance of accurate stability checks. So at this point, meron pong presentation or video regarding po sa Herald of Free Enterprise na ating pong papanoorin ngayon. So ito po siya.
On the 6th of March 1987, the shipping industry changed forever when the ro-ro passenger ferry Herald of Free Enterprise accidentally left port with her bow doors open. As she picked up speed, the bow wave grew, breaching the door level and flooding the car deck almost instantaneously. Just seconds after leaving the harbour, Herald of Free Enterprise was laying on her side, capsized on a sandbank, in an incident which tragically claimed the lives of 193 people. So what went wrong? How could such a seemingly simple error so quickly descend into one of the worst peacetime incidents in the history of commercial shipping? Herald of Free Enterprise was a Spirit-class roll-on roll-off passenger ferry commissioned by Townsend Thorenson in the late 1970s for the Dover-Calais route. Launched on the 21st of December 1979, she was one of three sisters with an overall length of around 132 metres and capacity for 1,400 people. The Spirit class have been designed specifically for the busy cross-channel route, with features such as forward and aft access to multiple car decks for rapid loading and discharging, and fast acceleration to get up to speed quickly for the short crossing. In her normal ports of Dover and Calais, the shore facilities included dual link spans where vehicles could get onto E and G decks simultaneously. It worked great when the ship was on a regular route. However, in March 1987, Herald of Free Enterprise was working between Dover and Zeebrugge instead. In Zeebrugge, they only had a single link span, which naturally slowed loading, and to make matters even worse, it couldn't actually reach the height of E deck if the tide was too high. To compensate for this, the crew would ballast down the forward end of the ship using a couple of forward ballast tanks which could hold around 310 cubic meters of water. The thing is, the ballast pumps could only deliver around 120 cubic meters of water per hour, so the ballasting operation had to begin 2 hours before arrival, and deballasting could run until a few hours after departure. Anyway, the crew were quite used to this, so on the afternoon of the 6th of March 1987, they completed loading as per usual and commenced discharging the extra ballast around 1740. Across the ship, the usual call for harbour stations summoned the crew to their respective duties in preparation for leaving the berth. The first officer left the vehicle deck where he'd been supervising the loading and headed towards the bridge, fully expecting the assistant boatswain to report for duty and close the bow doors before letting go. Unfortunately, the assistant boatswain was still asleep in his cabin, having slept through the harbour station's announcements, so no one noticed that the doors remained open. From the bridge, it was impossible to see the forward doors, and there was no remote indication panel telling them the status, so the master assumed all was good and commenced letting go. At 18:05, they left the berth and moved astern along the quay, swinging to starboard as they cleared the knuckle. At 18:24, they'd completed the harbour transit and were passing the outer breakwater, increasing speed in preparation for the crossing. By now, the ballast pumps had been running for around 45 minutes and had got rid of approximately a third of the ballast that they'd taken on earlier. This increased the height of the bow a little, but Herald of Free Enterprise was still trimmed by the head. To make matters worse, the increasing speed was actually sucking the ship lower down into the water due to an effect known as squat. Essentially, in shallow water, the flow of water around the hull gets constrained, increasing its velocity and decreasing its pressure. The lower pressure then sucks the ship towards the seabed, making it sit deeper in the water. Normally we're worried about squat in terms of a reduction in under-keel clearance, but on the Herald of Free Enterprise it caused an additional problem. The remaining ballast, combined with the squat effect from increasing speed, and the bow wave, again from the increased speed, meant that the water level ended up above the bottom of the open bow door. Within seconds, Herald of Free Enterprise was scooping up tons of water, lowering the bow even further and completely destroying her stability. The open nature of the vehicle decks on these sort of ferries quickly leads to a loss of stability in a flooding scenario thanks to a thing called the free surface effect. If you could spread the weight of water evenly across the deck, it would probably be okay, but ships roll around and water likes to flow downhill. This means that as a ship leans over even a little bit, additional water weight accumulates on the lower side, leaning the vessel even further over and moving even more water onto that side. On a vehicle deck, where water has the full width of the ship to flow, it doesn't take much water to add significant amount of weight right out on one side and cause a vessel to roll over completely. On the Herald of Free Enterprise, once the bow wave breached the open door, within seconds she started leaning heavily over to port. The initial sloshing did right the ship briefly, but by the second lurch, it was all over. She capsized onto her port side, coming to rest on a sandbar within a mile of the harbour entrance. The crew of a nearby dredger raised the alarm when they noticed the Herald of Free Enterprise suddenly plunging into darkness as their emergency systems flooded. Helicopters and nearby vessels rushed to their aid and rescued as many as they could, but despite their efforts, tragically, 193 people still lost their lives that night. Later investigations ultimately determined that there were 3 immediate causal factors. The assistant boatswain failing to close the doors, the first officer leaving the vehicle deck before confirming that the doors had been closed, and the master leaving port without knowing for certain whether the doors were actually closed. The thing is, as with any incident, you have to dig deeper to find out the underlying factors that led to the immediate causal factors if you want to prevent this same incident from happening again. For example, when we ask why the assistant bosun failed to close the door, we find that he was asleep in his cabin and didn't wake up with the harbour station's tannoy announcement. Dig a little deeper again, and we find that this same thing had happened before, with a different assistant bosun failing to appear for duty when the announcement didn't wake him. Now, we suddenly need to question the working practices in general and the culture from senior management that was causing exhaustion that led, on multiple occasions, to professional seafarers missing their call to duty. As for the first officer failing to confirm the door was closed, well, we need to ask why he left the vehicle deck before receiving visual confirmation. It seems that his harbour station's duty was on the bridge, so there is obviously some sort of mismatch between confirming the doors had been closed at the same time as undertaking his duty on the bridge. In terms of the master leaving port before confirming the doors were closed, again, when we ask why, a different story emerges. The design of the ship meant that it was impossible to see the doors, so third-party verification was required. An indication light would be the logical solution and had, in fact, been requested on the ships multiple times but was deemed non-urgent by upper management ashore. Their view was essentially that they're paying professionals to close the door, so shouldn't need to pay for additional equipment to verify that the job had been done. No, for departure, the master had to rely on reports from the crew members instead, but surprisingly, in the absence of any report, the company's instruction actually stated the master will assume at the due sailing time that the vessel is ready for sea in all respects. As you can see, although the immediate causal factors may have come from the actions of personnel on the day itself, the ultimate cause appears to have come from much higher up in the overall management and culture of the company. Indeed, when you look a bit further, you actually find these vessels had accidentally sailed with the bow doors open on numerous previous occasions, but they'd gotten away with it because other causal elements, such as the additional ballast and the effective squat, weren't present at the time. The Herald of Free Enterprise accident marked a turning point in the management of shipping companies, acting as a catalyst in the development of the International Safety Management, or ISM code. The code is basically all about creating a safer management culture within shipping companies, with specific personnel with direct board access given responsibility for the oversight of ship operations, as well as instructions for things like a safety management system containing standard working practices and regular audits and inspections to ensure that vessels are operated correctly. The Herald of Free Enterprise disaster not only exposed severe lapses in communication procedures and management accountability, but also highlighted the critical need for systemic change across the maritime industry. The tragedy served as a stark reminder that safety cannot be taken for granted and that complacency at any level can lead to catastrophic consequences. The subsequent implementation of the ISM code marked a significant shift towards a more structured and safety-focused approach in shipping operations. By mandating thorough oversight, clear communication and regular audits, the code has since played a crucial role in preventing similar disasters, ensuring that lessons learned from the Herald of Free Enterprise are not forgotten, but instead are integrated into the fabric of maritime safety.
Ever wondered where I fly? I'm reaching new heights in the blue skies. And if it starts to rain, I step in my airplane and start the flight into the blue skies.
The Herald of Free Enterprise is one of the most well-known stability-related accidents in terms of poor stability data. So, in 1987, the ship left port with its bow door open and poor ballast management. Water rushed in, the ship lost stability and it capsized within minutes. Kaya po nagkaroon ng 193 people na nawalang buhay. So these accidents showed that even small errors in loading or ballast can lead to disaster. So there are also other accidents linked to stability problems. Kagaya lamang po ng motor vessel thereby Shire sank in 1980 due to structural failure worsened by poor loading conditions. So kumbaga po, noong 1980, yung MV Derbyshire ay lumubog po dahil sa structural failure. And also, example din dito is yung Seawall Ferry na nangyari po last 2014, where improper cargo loading and insufficient ballast caused capsizing, killing over 300 passengers. So all of these cases remind us why using stability booklet correctly is a matter of life and death at sea. So to conclude, the stability booklet is one of the most important safety tool on board. It is not just a technical document, but a guide that protects the ships, the cargo, and most importantly, the lives of the crew and passengers. By ensuring stability calculations are always correct, accurate, we reduce the risk of accidents like capsizing or loss of cargo. So the key lesson here in our topic, which is the stability information or the stability booklet, is that stability must be part of our daily routine, whether during cargo loading, ballasting, or navigation. So when officers and crew apply stability principle consistently, the vessel remains safe, efficient, and seaworthy. Kaya po, always remember that safety first at sea begins with stability. So again, we are the group 3, and this is our presentation in terms or regarding the stability information or stability or the purpose of stability booklet. That's all.